We're now going to move on to Trevor Rushton. Trevor probably needs very little introduction. He's an excellent chap. I've lectured with him. I've been astonished at his knowledge. I've read his books. I'm a great fan. He's going to talk to us today about concrete defects and dilapidations. So what is disrepair? What is repair? So without further ado, Trevor, over to you.
Thank you very much, Paul, for that flattery. And thanks for inviting me along to such an august gathering of surveyors to talk about concrete. I did wonder why you wanted me to talk about concrete, but I'm happy so to do. Just our sponsor introduced a concept about new words that were meaningless, and I couldn't resist one that I learnt on Friday, walking around with a client looking at residential property, unusually for me, to conservatorise. And the lady concerned was quite surprised when I quizzed her on the meaning of that verb, but it means to build a conservatory. Total distraction. There's no doubt that concrete repairs is a massive industry, and it's a subject that causes a lot of vexation. It's a fiercely competitive industry. In 1990, the total cost was about 750 million. By the turn of the century, that sounds ages ago, it had gone up to 1 billion. I tried to find recent statistics of the level of repair, but let's just leave it as a big ticket. And it's actually sort of fairly simple concept made difficult by technology and probably a bit of ignorance, really. What I'm going to try and do today is move the slides on and cover some basics, some basic equipment to sort of, well, you probably already know it anyway, but just to refresh your memories as to why it all goes wrong, and then to look at some of the subject areas such as carbonation, such as chloride attack, such as HAC, and try and work out whether disrepair exists or not. Now, I'm not necessarily going to tell you the answers to the questions that I will ask, and we can debate them. Sometimes there is no black or white, there are shades of grey, so we have to apply the basic rules, and we've heard about the Nick's 5-point tests. All of that stuff applies here. I wanted to talk also a little bit about some other forms of construction, and I'll mention something on floor slabs as well, because that's sort of big ticket money when it comes to warehouses and industrial units, claims relating to those. So back to physics lessons. Why does steel corrode? If I take two metals, in this case zinc and copper, and dump them into a little bath of, well, we'll call it sulfuric acid for want of a better material, we get a current that starts to flow between the two. If we connect them electrically, we get a current, and one of them corrodes preferentially to the other. The cathode, in this case a bit of zinc, corrodes preferentially and gradually decays in favour of the copper. Now that's two different metals immersed in a bath. Why is that different from a piece of concrete? If I take a piece of concrete, it's perfectly possible to create a corrosion cell such as that with the same piece of steel as both the anode and the cathode. And in this case, the electrolyte is the concrete. How does that work? Concrete's solid, but it does contain moisture. So a current can flow through the concrete, believe it or not, and the degree of flow, electrical flow through that concrete, depends on its resistance. Well, that's news. And the resistance depends on its quality, how well it's been compacted, whether it contains voids, how wet it is, and all those sorts of things. So if I can create different conditions on my piece of steel reinforcement bar, So one bit perhaps dry, one bit perhaps wet, one bit exposed to oxygen, one bit not. I can create that corrosion cell as illustrated there. So I don't need two separate bits of metal. I can have one piece of metal, but I can put different conditions on it and create a corrosion cell. The speed of decay and the degree of it depends upon factors such as the resistance of the concrete. And if I've got something that's highly conductive, it will corrode more. So that's the nub of it, if you like. That's what it's all about. And we keep coming back to this basic mechanism. That's why it's important to dwell on it. Why doesn't corrosion occur inevitably? Well, when we make something out of concrete, it's quite a high pH environment, usually around about 12 to 13 pH scale, which is quite high. And what that does on a piece of steel is it permits the creation of I was going to say microscopically thin, but it's even thinner than that, passive layer, protects the steel. So in practical terms, if you thought, and this is a silly example, but imagine, say, a building such as Centre Point, Tottenham Court Road. And imagine the height of Centre Point is the diameter of the piece of steel reinforcement. I'm talking about a passive layer the thickness of a postcard on top of Centre Point. So it's very thin. So long as that passive layer is maintained, everybody's happy. But if something has a pop at the passive layer, we're in trouble. And there are two things that are likely to have a pop. Actually, there's more than two, but two main things that are likely to have a pop at it. And the first one is one of the most common gases in the atmosphere, carbon dioxide. And that in solution will attack the passive layer and disturb it. And when it does that, the concrete is at risk, or the steel is at risk of corrosion. The second agency is calcium chloride. And up until 1978, everyone merrily used to get their calcium chloride out and bung it in the concrete to speed up the setting time. Post 78, that's strictly taboo. And the reason for that is, if you put salt in, it creates conditions of high conductivity. And what did I say a few minutes ago? High conductivity equals potentially high corrosion rates. So the chloride will attack and disrupt the passive layer, leaving the steel vulnerable to corrosion. Chloride problems are particularly difficult to deal with, and I'm going to come back to those in a second. So I've pinched this from BRE Digest 144. It's quite an old document. There's a newer version now, which I think is 244. But the principle is there. And what I wanted to illustrate here was the progression of this reduction in alkalinity over a period of time. So if we start with I haven't got a pointer on here, but the top of the picture, the external surface, new building, good uncarbonated concrete, plenty of protection to the steel. But over a period of time, depending on the porosity of that concrete, the alkalinity drops. And that zone of carbonation gradually extends over a period of time and could reach a point where it reaches the steel. When the zone of carbonation has reached the steel, it doesn't mean that corrosion will occur. What it means is there is a risk of corrosion. So the first question really is carbonation disrepair? And you will often go out, when conducting a survey, you'll go and measure the depth of carbonation and also measure the depth of seal to see whether the steel's in the carbonated layer, whether there's risk, whether it's approaching it. It's particularly important for chlorides. I'll come back to that in a minute. If you've got a rebar close to the corner of a beam or something, it's got attack on two fronts, so it may be more vulnerable. If you've got cracks in the surface, the zone of carbonation goes further in, and you might end up with damage around the reinforcement part. So we've lost alkalinity, we've lost the level of protection afforded to the rebar. Doesn't mean the rebar is going to corrode. Is that disrepair? It's deterioration from a former better condition, Perhaps, one might argue that. It's the natural process of something getting old, weathering, normal age process of deterioration, if you like. But by itself, it's not actually led to any disrepair or any damage. So I would say probably not. Here's an example. I haven't got many juicy photographs of defects today, unfortunately, but here's some carbonation damage to a beam, column head. And you can see in this case probably didn't have much chance because there's very little cover to the steel. The steel has corroded, corrosion cells been set up, and the concrete's popped off. Fairly typical stuff. Fairly easy to repair. So we'll come on to repairs in a minute, but no particular obstacles there, and I don't think many people would argue with me that that probably is a good example of disrepair. It would find its way onto your schedule of dilapidations. Suppose the carbonation had extended back to the steel for the full length of the beam. So although we've got spalling and delamination here, we've got an area yet that has not yet deteriorated to the point where you've got to hack it off and to repair it. Would you be justified in saying, well, sorry guys, I've got to hack off all of that carbonated concrete and repair it? You might try and make that argument. Well, I haven't actually got a direct answer for you. My feeling is that going beyond that was probably not a repair that would be contemplated by the lease. But there's always shades of grey and the 5 tests and so on. But easy to concentrate on this bit. There is an argument to say you should carry on further than that. Would that be disrepair? Would that be a repair within the meaning of the contemplation of the parties? Possibly not, but it would depend on the circumstances. If the corrosion had taken place and it hadn't resulted in spalling, but nonetheless was there, that might be something that you would want to consider. I can't actually see that photo from here, so you've got a better shot at it than me. I put this in because it's actually a concrete deck. It's a car park ramp, so it's below a car park ramp. And we've obviously got some water ingress here, which has led to some staining. And there might be a bit of corrosion staining there. It's not absolutely clear. But you'll be familiar with the Post Office and Aquarius case, where we had water ingress into a basement due to a missing kicker. Well, here we've got water ingress into the area below the car park ramp due to the absence of waterproofing on top of it. So is that disrepair, and is there enough there to trigger a need to do something on the top of the ramp? Following the Post Office and Aquarius case, it was built like that. Ideally, it would have been built in a different way, but it wasn't. Can you see any evidence of disrepair there? Not really. There is some staining, I grant you, but at the moment, nobody's proved to me that we've got corrosion or deterioration. So I might argue Post Office and Aquarius in this case, and no need for repair, and certainly no need to start putting waterproofing on a ramp, changing the ramp to something different in a way. So, as I said, carbonation's fairly straightforward to deal with. And a typical spec would probably start off with hammer test, or cleaning it first, and then carrying out a hammer test to determine delaminated areas and so on. So first question, is the hammer test and the cleaning process something that you're going to charge, or the tenant's going to be responsible for, or the landlord if he's responsible for external repairs? Well, it's an essential part of the repair package because you can't really specify it until you've done that. But unless you've actually identified any disrepair as a result of that, then maybe you're not going to be able to recover those investigation costs. There can be, there's quite a lot of work involved in doing that. And actually, how do you do it? Because you need a scaffold up or you need cradles or something. So there's the first challenge for us. The actual repair system for carbonation is quite straightforward, really. No rocket science here. Break it out, expose the steel, clean it. Possibly prime it, depending on the system that you're using, put mortar back. And then what do? Do you leave it like that, or do you have to then put an anti-carbonation coating on it, or a levelling coat and an anti-carbonation coating? And my guess is that people like Sika and Mapei and all those Ronacrete will probably come with their nice little neat package that says we give you a warranty for 20 years or whatever, but you have to do this, this, this and this. As part of a repair, I can't see any problem with putting an anti-carbonation coating on. Although, hang on a minute, I've actually repaired the bit that has lost its alkalinity and I've put something back that's now alkaline. So what's my carbonation coating doing? I'm putting it on bits of exposed concrete that are already carbonated. What is the purpose of the anti-carbonation coating? Well, it looks nice, and it might reduce the rate of carbonation of the rest. But actually, I've got another 25 mil of cover there, so it's donkey's years before I even need to worry about that. So, question then, is the provision of the anti-carbonation coating a repair or not a repair? Is it protection for some future process deterioration that may or may not occur? Difficult answer to that one because it depends on the circumstances. Also depends on the nature of the building, where it is, location, proud foot and heart stuff. I think for the most part, if you've got a badly affected building that needs a lot of repair, there's justification for putting a coating on, if for nothing else, on to restore the appearance of it. But just be a little bit cautious. I had a case a couple of years ago where the schedule of delapse was requiring the tenant to, or attempting to require the tenant to put an anti-carbonation coating on, and we argued successfully that that was not repair. Now, that's all easy stuff. Chloride is a different kettle of fish, and the reason it's a different kettle of fish is because we have potentially conditions of high conductivity, and high conductivity equals potentially high corrosion rate, more damage, and so on and so forth. There are two issues. With carbonation, it's corroded, and usually when steel corrodes, it expands and forces the concrete off. If you've got sufficient chloride, you don't always get that kind of layered corrosion product. You can get something called pitting corrosion, where the steel actually pits, it disappears, it dissolves in it, if you like. So you might not know that you have a problem. You probably will do, but you might not know, particularly if you've got some pre-stressed tendons and that kind of thing. That's problem one. So you don't necessarily have a physical manifestation of the decay. You probably will. There might be some cracking if it's lost its strength. Problem two is this nasty little thing called an incipient anode effect. If you remember, you go back to my first slide and I said you can have a piece of steel, if you can vary the conditions on that piece of steel, you can get a corrosion cell. So chlorides, chloride-affected concrete, high conductivity. So we repair the area that's spalled. What do? Oh, we've set up a new corrosion cell between the bit that we've just repaired and the old bit. Process starts again. So incipient anode. So you're chasing your tail. You carry out repair on day one, and on day 365, there's evidence of corrosion still continuing. You haven't actually achieved anything. So chloride-affected concrete is difficult to deal with using, if you like, traditional repair methods. This is a waffle slab on a car park in Brighton, particularly vulnerable ribs there. And just a characteristic, while I mention it, you note how the concrete is stained. It's got that dark colour. There's a lot of staining to the concrete, typical of chloride attack, if you just want a sort of quick visual identifier. So, two things. Difficult to repair, and it may be suffering from pitting corrosion. So if you're now preparing your schedule of delapse, you might want to know or be able to sort of satisfy yourself that you've established the level of disrepair. Now, George Ballard, if you're going to his session this afternoon, is going to do some more on NDT, non-destructive testing. But I just thought I'd mention half-cell mapping because this is one method that you may employ, well, you'd certainly commission, you probably wouldn't do it yourself, where you are attempting to measure the risk of corrosion having affected the steel. In this case, you're measuring the potential difference. You're drilling a hole connecting electrical contact to the steel bar and then measuring currents. Will give you an indication of whether corrosion activity is taking place. And in a high area, such as we've got around the windowsill here in this office building and the mullions, might be worth some further exploratory work to determine whether or not we have corrosion. I've had cases where we've opened up and the rebar is missing. It's completely eroded away. So just be aware of that. So, chlorides. A few years ago, many years ago, too many years for me to remember, I prepared a lecture for one of the old weekend building surveying conferences on chloride extraction realkalization, which I thought was very sort of grand at the time. And makers were busy doing it on the old Hoover building out at wherever that is, West London somewhere. But I haven't seen much of that taking place, but it is still a recognised technology. So we can carry out repairs normally, and then we can sit back and wait for the inevitable to happen. Another method would be to use cathodic protection. And that's a system that is growing in popularity. But it is protection. Is protection repair? Might be. So we've got two broad systems. If you're into car parks and you're repairing those, you probably will come across these, the galvanic type, which are just like a little sort of zinc pellet wrapped in mortar with some wires sticking out of it. You open up the concrete, put this contraption in, attach it to the steel rebars, and it merrily, in a sort of somewhat uncontrolled way, corrodes sacrificially and prevents the steel from corroding further. So relatively cheap and cheerful. You haven't got much control over it. It doesn't last forever, and you can't really monitor what's going on. But it's a valid repair system where you've got high chloride. The other is an impressed current system where you put some anodes in. That could be a mesh, it could be a paint, it could be little probes that you insert and connect it up to a DC current. You put a current through the whole thing, and that reverses the corrosion currents that are occurring in the steel. A useful means, because it means you don't necessarily have to open up all of the chloride-affected concrete, or stonework for that matter, and hoik out those areas that are vulnerable to decay. So it's a great technique, and one that is gaining in popularity. It sounds a bit sci-fi, but you know it's quite straightforward, really. Its uses have spread beyond mere concrete, and here we've got I don't know where it is, it's a horrendous building one of our Leeds guys was looking at. I think this one is actually concrete, but it's the same applies to whether that was stone or concrete. This cathodic protection system would be a method, perhaps, of dealing with the corrosion of the steel frame in this building or the rebars. I don't think this one's listed, so you probably wouldn't bother. What are the options here? Face of the building such as this. Well, you can carry out entirely conventional repairs. You can hack it all off, you can expose the steel, repair it locally, put it all back together again. Or you could say, no, I'll do what sort of bare minimum. I'm going to grout all the cracks, stop the water getting in, that'll arrest the corrosion, and job done. Or I could do a mixture of all those things and add cathodic protection. And that system was the case that came up in Gibson Investments Limited v Chesterton, which involved a steel-framed building. Now, I know I'm digressing a little bit, but the principles are the same. We had here a corroding steel frame, common in London, certainly, and then from Manchester from about 1905 onwards. Usual stuff, Regent Street disease is what we call it here, corrosion of the frame. How are you going to deal with it? Well, we'll do some precautionary work. We'll stop the water getting in, or we will carry out wholesale repair, we can take the cladding off, put corrosion protection in, or we can put cathodic protection in. Now, cathodic protection does not repair the system. It doesn't repair the steel. It just arrests the corrosion, stops it getting any worse. So is that a repair or not? Is it simply a protection system, or is it a repair? And this was a sort of case that vexed the court in that question. And I think the eventual conclusion was that it could be a valid system, but I think you need to look at the merits of it in the round. What are you trying to achieve? 5-point test again. HAC, high alumina cement, concrete is one that's vexed people for many years, certainly since about 1974, when bits of it started to fall down, buildings started to collapse, although generally it was only the roofs that collapsed. What is HAC? It's a material designed by Lafarge back in about 1925. They were trying to get something that went very hard, very strong, very quickly, and had high chemical resistance. And it was used quite often in construction from the 50s and certainly through the 60s to the early 70s for the manufacture of precast beams particularly and some other components. And Pierhead were one of the major companies that supplied this material. What's the problem with it? The problem with it is that when you mix it up and it starts to set, it's an unstable product. Mineralogically, it is unstable. And gradually, the minerals in that HAC go through a process called conversion, which is where they change state. They move from the unstable state to a stable state. And associated with that change is a loss of strength. Concrete actually becomes more porous. Because it becomes more porous, it loses strength. Now that's all fine. If you've done your mathematics as an engineer based on a concrete strength of 21 newtons, that's fine, it works. But if you did your sums on a concrete strength of 50 newtons, say, that concrete reducing in strength could be embarrassing for you. So the question is the mere existence of high alumina cement, is that enough to sort of trigger disrepair? Does somebody need to do something about it? So if you've got a system that's working perfectly well, but it's lost its strength, does the tenant need to do something to restore that strength? Answer, probably not. But again, you need to go through all the process of investigation. In the cases that I've been involved with, and we were working on a shopping centre in Liverpool not so long ago, from an investment point of view, it's not very satisfactory, is it? You've got something that's definitely a bit dodgy. From an occupier's point of view, well, I can still use it for my retail purposes. It's not lost its strength beyond doubt. There's a system that you can use, BRAC rules, for working out whether you've got a problem or not, structurally. And if you work hard at it, you can prove that the floor shouldn't be there. It should have collapsed. Well, that's not very helpful to anybody. It's clearly still there. We had to prove it by loading out the floor with water tanks and measuring deflection. So the calculation method that BRAC rules give us proves that it doesn't work, but it's still there. We proved that it worked using water. So it would be hard to justify a requirement for anybody to do anything about it, and particularly if the building could still be used for the purpose that it was intended for. London Borough of Camden Civil Aviation Authority, this building could still be used as an office, but there was a question mark over the structure. A few years ago, I had a case on a building called Great Northern House up near King's Cross, where we didn't have HAC, but we did have a big question mark over the strength of the floor. And I was on the tenant's side, on the team, And the landlord was proposing to strengthen the floor using what was then a new process called carbon plate bonding, which is where you clean the surface off and stick a strip of carbon fibre using resin onto the floor, and that reinstates its flexural strength. Great. But where's the disrepair? We had, and from the landlord's point of view, he had an investment that was distinctly dodgy because he had to put floor loading notices up everywhere. From the tenant's point of view, well, I'm using it as an office and it's fine. You're telling me that an office should be, 2.5 plus 1 floor loading. Actually, I don't need anything like that. It's working fine. I've got no deflection. I've got no disrepair. You can go whistle. Didn't stop it going all the way to the High Court. Regrettably, they settled it before we got an answer, but it would have been great fun to have gone through that process. Go back to my HAC. If we have got deflection, if we've got a serious problem structurally, sticking carbon fibre on the underneath of it might be one way of dealing with the problem. Slightly older form of construction, wood wall slabs as permanent shuttering. You're all familiar with that, I hope. The big issue is that we get voiding round the reinforcement bars. So it's going to be in from the start, built like it. What does that do? Does it compromise strength? Probably not, but it does compromise fire protection. Might arguably compromise corrosion protection, but I'm not sure about that. From investors' perspective, wood wall slabs permanent shuttering is a bit of a no-no. Is it disrepair? Probably not, actually, because it's there, it's not leading to any problems. What would be the case if you had a fire and there was more extensive damage? I don't know, interesting conundrum. Similarly, hollow pots. Deleterious materials and all that always go on about wood wall slabs. They never mention hollow pots, but the problem is exactly the same, and that is the risk where you've got spacer tiles, the risk of voiding around the reinforcement concretes. I got involved in a case in Holborn a few years back where a tenant moved in. It was can I say this? Well, it was an old Woolworths store, long gone. Tenant took the upper parts and was converting to offices. District surveyor came along and said, can you prove to me that we haven't got voiding, because I'm worried about fire protection. No, we can't. Investigated it. Yes, we have got voiding, needed wholesale repair. So there was an almighty row about who was responsible for hacking off all of the spacer tiles and putting in gun-applied concrete afterwards to restore the fire resistance. But it wasn't disrepair. It was always built like that. I just wanted to put this in because Twinmar, you all knows about roof lights and stuff, but it did also cover condition of the floor and the concrete floor, and there was some commentary about whether if the aggregate in the floor was exposed, it was disrepair, and it was, and the landlord was entitled to recover. So that leaves me an introduction into floors, ground-bearing slabs. Now, I was rummaging through the internet, as you do, prior to this. I was actually looking for statistics to throw at you. Didn't find many. But there were a few contractors that were reporting a huge increase in the number of concrete slab repairs. I don't know why, whether it's because as surveyors we've come sort of more alive to the problems. This was an interesting case. This was actually a warehouse that, believe it or not, was only a couple of years old. And what we're looking at here is the sawn contraction joints in the floor. You know what this is all about. If you've got to control shrinkage, so you want cracking to occur where you want it. So before the concrete is fully set, you cut in a 5mm joint, a few millimetres through, 50 mil through the depth of the slab, with the hope that when you get the shrinkage, it will crack there and nowhere else. That's fine. The trouble is that concrete does shrink, and it particularly shrinks during its first few months of life. So the filler that you put in that joint needs to be able to accommodate shrinkage. And that shrinkage is going to be greater during the first few months of life than it is after the first few months of life. So What is supposed to happen is that after or at the end of the defects liability period, there should be a provision in the contract, one hopes, if it's specified correctly, for the contractor to go in and remove the initial flexible sealant and replace it with something harder, what's called shore hardness is better. Now, that didn't happen in this case, so the tenant was left with the original flexible sealant that should have been replaced. He still had it. And it was a parts warehouse. They supplied components for automotive factory, so it was constant use and big sort of things being dragged across the floor. Well, you can see that it started to break down quite badly there. Had the sealant been replaced with something with a higher shore hardness, perhaps it would have given more support to the edges of that crack and we wouldn't have got that level of deterioration. So we're kind of into the old chestnut of inherent defects and stuff, which obviously was argued without much success, because it's still quite firmly in our view that the tenant's responsible for repair, but we had the usual arguments about that. But it's an interesting one to be aware of. Maybe if you're representing a tenant taking a lease on a building, on a new building, or even one, well no, let's say a new building, is there provision for replacement of these joints? Because doing several hundred metres of that kind of repair is quite expensive. If you don't like conventional reinforced slabs, you use steel fibre reinforced, because you can lay much larger bays in one go. These are sort of highly engineered floors. They're not just subject to normal mathematics, if you like. They're a particular product. And this was actually a floor on a very, very large distribution warehouse in Belgium. This wasn't a delapse claim as such, but we were involved in a wrangle between landlord and tenant over the cracking. And you can see that there's what I've termed very extensive map cracking in the surface. Why is it there? Well, because when you power float the floor, all the sort of cement-rich stuff comes up to the top and it shrinks and it cracks like that. Is it disrepair? I think probably not. I think it's just, it's part of what you get. It comes with the territory, if you like. I would say that in this particular building, possibly due to construction methods, the map cracking was much more severe than I'd seen anywhere else. And we were concerned that over a period of time, you would get more wear. The little individual lenses would pop off and you get deterioration and so on and so forth. In the end, landlord agreed to broadcast a very thin resin over the whole floor to help seal those cracks and prevent deterioration. I've no idea what the law of delapse is in Belgium, but this was an interesting case. Is cracking like that disrepair? Possibly not. Perhaps it could reach a certain level where you do need to do something with it. Perhaps that is good enough to trigger an obligation. And then almost finally, another warehouse in Belgium where we had some quite profound cracking in the floor. And this was sufficient to cause great alarm and despondency, and the tenant started to withhold rent. Now, again, we're talking Belgium, and this is not a UK issue, but the principles are the same. So why have we got all this cracking? And they put resin in and tried to repair it. The big problem was that as they put their materials handling equipment over it, that sort of shook around a bit. They lost a pallet. There was concern over deterioration and so on and so forth. So first off, why is it cracked? Is it just shrinkage? What we found is that they put their racking in, and this is serious racking because it went up about 10 lifts, with all their bottles of vinegar. It was a food distribution warehouse. There was quite a big load on these legs. They'd gone in fairly early, so they kind of pinned the floor in place and restricted its ability to do what it wanted to do, which was shrink, and so therefore it had cracked. But we went a bit beyond that, and we found that the slab, whereas it had been designed at 135 millimetres thick, steel fibre, was actually only 113 in places. And logic says to you, well, if we needed 135 and we've got 113, it's not going to be strong enough. And we ought to be restricting the amount of load that's put on those racks. Well, what do you do then as a landlord? You say to your tenant, sorry, you've got to take out the top. You can't use the top lifts of your Dexian racking. And there's another big row brewing up. What we actually found eventually was that the strength of the floor was okay. We managed to prove, the contractor argued that our calculations were wrong, which was fair. We got a very heavy crane, parked it in the warehouse and jacked it up to see if the floor would deflect, and no, the floor didn't deflect, so yeah, okay, fair dues, it's working. What we'd actually found was that the site, when they'd cast the concrete, and had wheeled trucks going across it, so you had little depressions where the wheels from the trucks had gone. So you had zones of thick floor, thin floor, thick floor, which obviously affected how it all shrunk and moved around. So that was a rather long and rambling way just to illustrate some of the problems that you get with steel fibre reinforced floors, or on any floor actually, and perhaps some of the wrangling as to whether you've got disrepair or not. Summary and conclusions. I've explained how corrosion works. Electrochemical problem. With chloride, you might have to deal with it electrochemically. Possibly a more robust form of repair. Concrete deteriorates, it carbonates by itself, it loses protection. Is that disrepair? Don't think it is. What about high levels of chloride? Yes, you could have a problem there, particularly if you've got pre-stressed concrete. The thresholds for chloride content are much lower for pre-stressed concrete. What are you achieving by the repairs? Is your level of repair more than that was contemplated? Are you trying to reinstate 50-year life as opposed to just get the building limping through? Or what is the standard of repair that you've got to achieve? And remember that precautionary work, that reinstating life or protecting against further deterioration, might make good sense on the balance sheet, but is it necessarily repair? Answer, possibly not. Paul, I make it about 5 seconds before 11 o'clock.
Yeah, I've got a 5-second question for you. We've had a few questions come through. First one, is carbonation, could it be argued it's an inherent defect?
Well, there's no such thing as an inherent defect really in Dilaps, is there? So, answer, don't like that question. It's not going to get you very far. But it is something that goes wrong. It will happen. It's part of the normal process of ageing and deterioration of concrete. So my feeling is it is not in itself disrepair, but it could lead to problems, in which case you may well have an obligation to do something about those problems. Does that make sense?
Good. I'll try another couple of questions that you won't like then. Do you feel that often used epoxy coating to warehouse floors is a genuine method of remedying disrepair, or is it just for aesthetics?
I think, again, you need to look at the circumstances. You've created yourself a nice little repair liability for the future, whether it's epoxy or polyester. Epoxies tend to form more of a surface skim and therefore are easily flaked off. You're covering up something. But on the other hand, what are you trying to achieve by the repair? Are you making it look nice? Are you stopping it dusting? If you've got a dusty floor or one that you've heavily patch repaired, it might be a means of achieving serviceability. So I think that's a difficult question. I quite like that question, but it's a bit more of a difficult answer.
Good.
I think you need to look at the circumstances.
Okay, well, a difficult question, easy answer,
yeah,
difficult question.
Yeah.
Okay, and finally, is resin grout injection below industrial floors a way of overcoming, if you had the problems, a thin floor or voids beneath? Is that something that you would?
Yeah, we have looked at that, and I think in certain circumstances it can be. And by this you mean the stuff that expands.
Yes.
Yeah, so you drill a hole. If you're not familiar with it, if you've got an area of floor that's sunk, you can sometimes jack it back up again using an expanding chemical. I think actually it's a foam rather than whatever it is, a gubbins that expands and pushes the floor back under controlled conditions. I've been tempted to use it. We had a floor out in Dagenham. It was a coin warehouse, above all things, but built on peat. And the floor had moved quite badly there. And the problem with that system in that case is that for it to push the floor back up again, it's got to jack off something that's quite firm. And so we had loads of peat, and you know, it wasn't really going to work there. So in that case, it was a rebuild, or potentially a rebuild. In other circumstances, it might be a valid thing to do.
Thank you. Before I give you the housekeeping notes, which you will need, could we thank Trevor, who managed in one sentence to use the words High Court and great fun in one sentence. Well done. Never seen that happen at one of these conferences. Could we thank Trevor, please? The usual.